Well, this is it. The moment we've been building up to. All of our work with derivatives, integrals, and limits has been preparing us for this moment. So now it's finally time to bring it all together and prove the fundamental theorem of calculus. We've now used limits to precisely define both the derivative and the integral. And we've seen how limits help us make convincing arguments via some valuable theorems. Now we're going to turn our attention to arguably the most important theorem in the entire course, which is why it's called the fundamental theorem of calculus. Remember that we just saw how to calculate integrals as a limit of Riemann sums. It certainly works, but I think you'll agree that the process is pretty complicated. And what's more, the argument we gave only generalizes to basic polynomials. It's not obvious how we could modify it to work with roots, or trigonometric functions, or just about anything else. But that's where the FTC comes to the rescue. It establishes that derivatives and integrals are in some sense opposites of each other. And that's what lets us calculate definite integrals by finding an antiderivative, plugging in the endpoints, and subtracting the results. We gave kind of an intuitive reason why the theorem worked, in terms of nudging areas by an infinitesimal amount, but that argument was admittedly kind of hand-wavy. There were a lot of questions it left unanswered. But that was a deliberate choice. For many things in math, I firmly believe that it's important to get a good feel for what you're learning about before you get into the minute, specific, nitpicky details, especially when it comes to something as subtle as calculus. That's actually a big part of why I've chosen to put limits at the end of this course, when usually in most textbooks, they're covered at the very beginning. To use an analogy by Paul Lockhart, putting limits at the beginning of a calculus course is like learning how to read and write music on a page before you're allowed to hear it or sing it. The music came first. The notation came later to help us be more exact with communicating it. Likewise, the overarching ideas of calculus have been around for a very long time. Slopes, areas, curves, and small changes. But actually defining those ideas rigorously is hard. And to come up with the right definition, you kind of have to know what you're aiming for. But now, I think we're ready. It's taken a lot of work, but we finally have all the pieces. Now we just have to put them all together. Now let me be clear here. When I say we need to put the pieces together, that includes you. I'm going to lead you through the argument, but as we go, you'll need to figure out why we're taking some of the steps that we do. In particular, there are 7 statements that will be used in some order throughout this argument. 2 statements about derivatives, 2 statements about integrals, and 3 statements about limits. Let's take a moment to look at each one. First, we've got the limit definition of the derivative, the limit of the slope as the change in x shrinks down to 0. Second, we've got the relationship between continuity and differentiability. If a function is differentiable, then it has to be continuous. Although the converse isn't necessarily true. Think of the absolute value function. A function that's continuous may not be differentiable. Third, we've got the additive interval property for integrals, letting us split up an integral into 2 integrals on adjacent intervals. Fourth, we've got a useful comparison property for integrals. If one function is less than or equal to another, then the first integral is also less than or equal to the second integral. If you think about this in terms of area, it should make intuitive sense. Fifth, we've got the limit definition of continuity. In order to be continuous at a point, the left-hand limit, the right-hand limit, and the value of the function at that point all have to match. Sixth, we've got the squeeze theorem. When a function is squeezed between 2 others, and the outside functions approach the same limit, the inside function is forced to go to that same limit. And finally, seventh, we've got the extreme value theorem. If a function is continuous on a closed interval, It has to reach an absolute minimum and an absolute maximum on that interval. Each of these 7 statements will be useful at some point in the proof. It's going to be your job to figure out when and how. Write them down as you see them. You'll be asked at the end what order they were used in. Now let's also state the theorem we're proving a little bit more carefully, along with a few assumptions I left out the first time we looked at it because we weren't quite ready for them yet. Suppose we have a function f that's continuous on the closed interval from a to b. And then suppose that we define g to be an area accumulation function, specifically the integral from a to x of f of t dt. Notice that a is a stationary value, while x is free to move as long as it's between a and b. Then that new area function g is continuous on the closed interval a to b, and differentiable on the open interval from a to b. And most importantly, the derivative of g is f. So that means the area accumulation function g is an antiderivative of the original function f. Okay? That's the theorem. Let's prove it. So we'll start with the integral from a to x, and then we'll nudge our moving endpoint by delta x, keeping x plus delta x within the interval from a to b. Let's see if we can find a way to rewrite that area from x to x plus delta x as g of x plus delta x minus g of x. We'll use our definition of g to write that as a difference of 2 integrals. And then we'll rewrite the first of those integrals, which goes from a to x plus delta x, as a sum of 2 integrals. The first one going from a to x, and the second one going from x to x plus delta x. Now we've got 3 integrals, and the first one cancels with the last one, so we're left with the integral from x to x plus delta x. So what we found is that g of x plus delta x minus g of x is equal to the integral of f of t dt from x to x plus delta x. Next, divide both sides by delta x. And let's assume for now that delta x is positive. Now, since f is continuous, we'll let little m be the absolute minimum value that we know f reaches on the closed interval from x to x plus delta x. And we'll let big M be the absolute maximum value it reaches. And we'll suppose that the absolute minimum happens at u, that is f of u equals little m, and that the absolute maximum happens at v, that is f of v equals big M. Both of those happen between x and x plus delta x. Now, since f of t is always between little m and big M, we can show that the integral of f of t dt from x to x plus delta x is bounded below by little m times delta x and above by big M times delta x. Those are the areas of 2 rectangles. Let's rewrite little m and big M as f of u and f of v, respectively. And then let's divide throughout by delta x. Now that part in the middle should look familiar. We just showed that's equal to g of x plus delta x minus g of x, all divided by delta x. So we'll replace one with the other, and we end up with this inequality. By the way, if delta x were negative, the argument would go a little differently, but the idea would largely be the same. Now, let's shrink delta x down to 0 using limits. What will happen to f of u as delta x approaches 0? Well, since u is stuck between x and x plus delta x, when delta x shrinks down to 0, u will approach x. So the limit of f of u as u approaches x has to equal the function value f of x. Think carefully about why that limit has to equal the function value. And for the same reason, the limit of f of v as v approaches x also has to equal f of x. So both of those outside limits have to equal f of x, which then means that the inside limit also has to equal f of x. And that inside limit is precisely g prime of x. So what we've shown here is that g prime of x equals f of x. There is admittedly the possibility that x could have been one of the endpoints a or b, but that's not too big a deal. We can always reinterpret those limits as one-sided limits if we need to deal with that. And by the way, the fact that we're able to talk about g prime at all means that g has to be continuous. And there we go. We've proven everything we set out to prove. Our area accumulation function is continuous on the closed interval from a to b, and differentiable on the open interval from a to b. And most importantly, its derivative is our original function, which means that the area function g is an antiderivative of our original function f, QED. Think about just how many things we needed to put together in order to be able to make this claim and be convinced that it works for any continuous function. Now I hope you see why this result deserves to be called the fundamental theorem of calculus, and why we've been building toward its proof little by little throughout this series. So now what? Where does the study of calculus go from here? I'd like to give you a small taste of what the future holds. First of all, there's a lot more left to talk about with integrals. We only saw the most basic examples, the ones that are essentially just recognizing a derivative of a function you already know. It's been said that while differentiation is a science, integration is an art. With derivatives, you just have to figure out which rule to apply and then chug through it. But since integrals involve working backwards, it's not always clear where to begin. You have to look at what you've got and play around with it a bit to try to find a technique that might work. The same goes for differential equations. Separation of variables is only one of many techniques for solving them, and usually there's an entire course dedicated to how to get a feel for which technique might work. And differential equations show up all over the place in science and engineering, so it's not like you're just shuffling symbols around. They're really useful for real-world applications. There's also a lot of interesting things we can do if we extend and refine the ideas we've already studied in calculus. For example, we could continue the idea of linear approximations, finding better and better approximations of functions by using polynomials of higher and higher degree, quadratic, cubic, and so on. Eventually considering infinite series to approximate functions as closely as possible, though then we'd have to talk about when those series converge in the first place. Or we might look at how the ideas of differentiation and integration extend to functions of multiple variables, allowing us to think about how they apply to solids, vectors, space curves, and surfaces. We can even see what happens when we introduce imaginary and complex numbers into calculus. You'd think that would make things way more difficult, but it actually turns out that complex numbers work beautifully with calculus, making certain calculations easier, and finding surprising applications in science, engineering, and other fields. Finally, we could take a deeper dive into the logical underpinnings of calculus, and rigorously prove why everything we've done in this class works. There are a lot of claims that we've admittedly left unproven, so that we could focus on more intuitive ideas and applications. But if you're taking real analysis, you leave nothing unjustified, tackling the questions of what real numbers actually are, and why their properties allow you to do calculus in the first place. Though, take note, real analysis isn't the only way to justify calculus. There's also a relatively new branch of math called non-standard analysis, which takes the infinitesimals we've talked about multiple times throughout this class and actually makes them rigorous by constructing a brand new number system of hyperreal numbers, full of new worlds, some infinitely large and some infinitely small, just waiting to be explored. This all might sound intimidating, but it's also fascinating. Just keep in mind the problem-solving techniques I've been introducing throughout these videos. Remember, memorizing formulas and procedures isn't enough. You have to understand them. If you adopt a mindset of focusing on concepts, looking for patterns, and keeping a sense of awe about the infinite, I think you'll be in good shape.